Thank you, Sheldon. And let me add my welcome to everyone. We're delighted you're here with us this morning. I'm also delighted that I'm here this morning because it gives me the opportunity to tell you about some of the really extraordinary things that are happening in the Heart and Vascular Center. Now, as I relay my stories this morning, I want you to keep in mind one premise that underlies everything that I'm going to talk about, and that is the critical importance of teamwork. It underscores everything that we do, and we could not be successful if we didn't adhere to that principle. Now, there's an old concept in academic medicine called bench to bedside. Bench is on one end, and the bedside and the patient are on the other. When we start out, we have an idea, a new idea, or a new observation. We have to develop it, we have to test it, we have to perfect it, and then hopefully someday we apply it to our patients to improve the health of the patient. We're going to start at the bench and we're going to work our way up to the other end, to the bedside, to give you a flavor of the range of things that we're involved in and that each is important. So let's start at the bench. We're going to start talking about heart cells, single heart cells, okay? Bear with me. When you have a heart attack, heart cells, heart muscle is damaged. Some of those heart cells recover and go back to normal function, and some of them die. The more cells that recover, the more likely it is that the patient will recover. Very important stuff. For decades, scientists have been studying why is it that some heart cells live and some heart cells die during a heart attack. This is Dr. Jinji Ma. Dr. Ma leads a team of investigators at the Davis Heart and Lung Research Institute who began studying this problem a couple of years ago, several years ago. They discovered a protein called MG53. Now, they wondered what MG53 did, and they studied it, and they discovered that MG53 seemed to have something to do with repair of heart cells during injury. All right? Now imagine for a minute that I walked up to you and I stabbed you with a pin. It would hurt, you might bleed a little bit, but you probably wouldn't die. Well, heart cells are the same way. You can stab a normal heart cell with a needle and it repairs itself, it survives. But Dr. Ma's team found out that if you take cells and you block their ability to make MG53, and then stab them with a pin, the cell dies immediately. So clearly, we need MG53 in order to repair ourselves and in order for ourselves to remain alive, all right? Now, the next question, though, was how does MG53 do it? Let me show you a little movie here. This is a cell. This cell has been labeled with green fluorescent dye so that the green dots are the MG53. Now, if we could play the video, what we're going to do is stab the cell on the left side of the screen, and you'll see what happens to the MG53. It all ends up at the site of injury. It forms a seal over the hole that was created by the injury. It's the first line of defense to save the cell. So it's critically important, and that's how it works. Now here's the really fascinating part. Dr. Ma's team was able to clone the gene that makes MG53 and basically manufacture MG53. And what they have found is that if you administer, I've got some here, you can see me afterwards, make a deal. Sorry, Jinji. What they found was that if you administer MG53 during an experimental heart attack in an animal, it greatly reduces the amount of heart damage. In fact, in some cases, it completely eliminates the damage. So this is really exciting stuff, really potentially important stuff. But this is still at the bench. It's a long pathway and a lot of potholes to go before we get to the bedside. So stay tuned because this will change things. So that's the bench side of things. Let's move to the other end of the spectrum and let's talk about the bedside and what we're doing today to help our patients. Does anybody know what this is? It's not a fishing lure. Okay. This is the world's smallest pacemaker. Now, I think you're all familiar with pacemakers. Pacemakers are, the standard pacemaker is implanted. We make a little incision. It's surgical. We implant the battery underneath the skin. We connect wires to the pacemaker. We thread the wires through a vein down and screw them into the heart. This pacemaker doesn't require any of that. It's delivered by a catheter directly into the heart. Got to remember my pockets here. And it connects, you can see the little tines on the end, it connects with the heart muscle, and in doing so, it paces the heart. I've got one I'll show you later. This is Dr. Ralph Augustini. Dr. Augustini leads the team of heart rhythm doctors at Ohio State, and he was instrumental, along with a team of engineers and scientists, at developing and perfecting this particular pacemaker. In fact, the second one of these that was ever implanted in the world was implanted here at the Ross Heart Hospital by Dr. Augustini's team. They're now working on a version of this device that has additional capabilities that will be particularly valuable for our patients with congestive heart failure. So speaking of congestive heart failure, let's talk about that next. Before I tell you what this is, let me give you just a little bit of background. We're going to talk about heart failure now. One of the biggest problems patients with heart failure face is the problem of readmission. And by that I mean, try as they might, they take their medicines, they watch their salt, they weigh themselves, they still sometimes will accumulate fluid, get short of breath, and have to be readmitted to the hospital. This device, which I also just happen to have right here, is a pressure monitor. It's delivered into a vein in the lung by a catheter where it floats out and sits there inside the blood vessel, where it monitors the pressure inside the lung. It turns out that the first earliest manifestation, usually, of patients getting into trouble is an increase in that pressure. So by monitoring the pressure and by signaling a computer, the patient's physician is alerted at a very early stage that the patient is on the verge of getting into trouble. The physician can intervene, the patient can be treated medically, and oftentimes an admission can be avoided. This is our very own Dr. Bill Abraham. Bill is the chief of our division of cardiovascular medicine, and he has been a pioneer in this technology for over a decade. A few years ago, Bill led a team of international investigators that studied how effective this technology was, and they were able to show that using this device, they could reduce the rate of readmission from heart failure by almost 40%. More important than that, the patients felt better because they were being monitored and they were being treated early on. This is my definition of intensive care, and it's really been an exciting development in what we have to offer our heart failure patients. Now, it happens that heart failure and heart rhythm problems are two of the things at Ohio State that are probably our strongest areas. What you might not know, though, is that the two conditions often coexist in the same patient. One problem begets another. If you have heart failure, you're often likely to develop heart rhythm problems and vice versa. One such patient that exemplifies this overlap is this individual here. This is Greg Ruff. Greg is one of our patients, and he's cared for by both our heart failure doctors and our heart rhythm doctors. Now, Greg's story is a long and involved one. It starts way back in high school. Over the years, he visited many physicians, he went to many hospitals, he was seen by institutions around the country. One day, a couple of years ago, while he was being evaluated in a genetics clinic, one of the counselors looked at Greg and said, "You know, you really should go see the people at Ohio State. I think they might be able to help you." And that's what Greg did. And this is Greg's team here at Ohio State. On the left is Dr. Steve Kalbflesh. Dr. Kalbflesh is one of our heart rhythm doctors that took care of Greg's electrical problems. And then he introduced Greg to the gentleman at the top, Dr. Ray Hirschberger. Ray is one of our heart failure physicians, and they worked together to make sure that Greg got optimal care for both his heart rhythm and his heart failure problems. Now, the other team that's represented here are our human genetics team, and that includes Dr. Hirschberger, and then Dr. Amy Sturm on the right, Dr. Anna Morales down below, and Dr. Peter Moeller, who's the director of our Davis Heart and Lung Research Institute. They further characterized Greg's problem and were able to demonstrate that Greg's problem was in fact due to a genetic mutation. The gene is called lamin. It's a structural protein, and it explained much of Greg's problems that he had faced with over the course of his lifetime. Now, knowing that information doesn't really help Greg. Greg already has his condition, and we're providing him with the optimal care. But it's important nonetheless for this reason, because by knowing that information, we can help his family, and particularly his children. Greg has 3 lovely children. This is a family photo. And by knowing whether the gene is passed on, we can help monitor them, we can counsel them, we can help them in the prevention of heart disease, and we're there to detect it at the earliest stages. Greg and his family are actually with us today. Greg, can you wave to us? Greg does not look like he has heart disease. He's still exercising, he's still working, and he's a great advocate for what we do at the Ross Heart Hospital. So, exciting things are happening, remarkable things every day at the Wexner Medical Center. The treatments that we have available today are better than they've ever been. The things that we're learning and discovering will improve the lives of our patients in the future and their families, very importantly. I talked a lot today about teams and the importance of teamwork. I want you to know that you're part of our team too. You're a critical part of our team. And we're all in this together, and we couldn't do what we do, and I couldn't have told the stories I told without your support. Now, the people back at the Ross and the Davis told me today, or told me yesterday, or told me the last few days, that I couldn't end today without one last comment. And that simply is that from the bottom of our hearts, we want to say thank you for your faith, for your vision, and for your generosity. Thanks very much.
Well, thanks, Tom. And in case any of you thought this isn't live, it is. Dr. Drake was showing me the radar. There is a storm passing through. I've been...
Back up, you're going to get wet.
I've been assured that most of you will survive if you stay here and listen. So, can you hear me in the back? Yeah, good. All right. I'm going to persevere. All right, Tom.
Yes.
That was fascinating. I wonder if you could expound a little bit on the interaction between arrhythmias, heart disturbances in terms of rhythm, and heart failure, and even genetics. Could you tell us a little more?
Sure. So, too often we look at these things as separate problems. Whether we're talking about clinical care or research, we think of them as separate entities. We have our heart failure team over here and our heart rhythm team over there. The next wave of breakthroughs in this area is going to require those groups really working together, both from a research standpoint and also from a clinical standpoint. And the kind of things that we're going to discover that help that large group of patients with both conditions will be through the interaction of these two groups. And it's really going to be exciting, and we want to be a part of that, and we will be a part of that. Again, it comes down to teamwork and thinking about things in novel ways. Genetics underscores a lot of those problems, not all of them. The more we learn about genetics, the better we'll be at being able to care for that very important group of patients.
Thanks. Warm round of applause for Tom Ryan.
That's CardioMEMS. CardioMEMS. That's the device in the lungs.
Is that like a Swan Gans?
You can put it, yeah, exactly, like a,
Yeah, see?
that you can take home with you.
I still remember. Thanks, Tom.